This is Unit 6, Video 7. In this video, we will take a look at the famous phase diagrams. Now, a phase diagram actually shows the phases, or the states, of a substance, the three states of substance, solid, liquid, gas, at various pressures and temperatures. And it looks very much like the vapor pressure curves we looked at just in the previous video. In fact, the vapor pressure curve essentially exists in this area right here. And or it kind of looks like a slightly a version of it. What you have here in a phase diagram is you have a graph made between the temperature on the x-axis and the pressure on the y-axis of a given substance. Now, the three phases on here are solid, liquid, and gas. Here they are. And you can think of it as you going from a solid to a liquid to a gas as you increase temperature. So as temperature increases this way, you have to go through the three phases. You can also increase the pressure, and you can go from a solid, usually from a gas to a liquid to a solid. So usually as you increase this way, you can kind of see the progression from a gas to a solid. As you increase the pressure, you're pressing the molecules closer together, and they eventually become a solid. So we're going to take a look at all the different features of this diagram in the next slide, and I'll point out some important parts and important terms relating to the phase diagrams. Every substance has its own phase diagram. Just like, remember, we had a heating curve for every substance, we have a phase diagram. We can produce a phase diagram for every substance. Quite a bit of data goes into producing this, and it's actually more detailed than a heating curve. Heating curve usually just has temperature. This one has pressure to deal with as well. But what you can see just off the bat is whether something is a solid, a liquid, or a gas depends not only on temperature, but also on pressure. This is a very important concept to understand. So you can make a substance into a gas by adjusting not only temperature, but also by adjusting pressure. So let's take a look at it a little more closely on the next slide. So what we have here is we have the lines, the transition lines between a solid and a liquid. That's this boundary here. So if you are to go across this boundary, then you're either melting or freezing. So if you're going from a solid to a liquid, we call that melting. Back over the other way, we call it freezing. Now realize that you can go across this boundary by adjusting temperature. So you can increase the temperature, and you're now crossing this boundary. But you can also do so by adjusting pressure. So for example, if you're at this point, say at a certain pressure and temperature, and if you increase the pressure going up, you'll actually transition from a liquid to a solid. Likewise, if you're a solid and you decrease the pressure, you can actually transition into a liquid. So here you can go melting, freezing now by reducing or increasing the pressure. Same thing happens across this boundary here, the liquid-gas boundary, and you can heat up the liquid and we undergo vaporization. You can cool the gas, we can undergo condensation. But you can also go up and down using pressure. So for example, if you're a gas here and you increase the pressure, you'll become a liquid. If you're a liquid at this point, you reduce the pressure, you'll become a gas. So you can undergo those phase changes just by adjusting the pressure. And lastly, this portion here, at low temperatures and low pressures, you can undergo sublimation. So you can go directly from a solid to a gas, and you can undergo deposition from a gas down to a solid. Again, by increasing or decreasing temperature. And you can do the same thing by increasing pressure or decreasing pressure. So you can undergo any phase change by adjusting pressure, and you'll achieve any phase doing that. Now, a few things to look at here, or a few points. This one here is called the critical point. Now, the critical point is a point at which the gas and the liquid essentially kind of fuse together and become one substance. This happens at very high temperatures, and it happens at very high pressures as a rule. So high temperature and pressure. Eventually, the liquid and the gas phases kind of blend into one and create something called a supercritical fluid. This fluid can flow. Usually we think of liquids flowing, but it can also get compressed, and usually gases are the ones that are compressed. So you essentially have both of these properties in this fluid, and it's no longer a liquid or a gas. It's like a combined version of a liquid and a gas, and that's the idea. So this is called the critical point. Every different substance has a different critical point, and usually the critical point is connected to the strength of the forces. So if you have very strong intermolecular forces, you'll have a very high critical point. If you have weak forces, you'll have a low critical point. The other point on here I would like to point out is something called the triple point, the T here. The triple point is a point on the graph under a set of temperature and pressure conditions where all three phases of matter coexist. So all three phases coexist. We actually say that all three phases are in equilibrium. In equilibrium. Which means you can actually get yourself a container of a substance. So in this container, if you adjust the pressure and the temperature just right, you'll get the solid version of that substance, the liquid version of that substance, and the gaseous version of that substance. And they'll actually transition from one to the other. And we'll show you a few videos of this being done. You have to have some machinery to be able to adjust the pressure suddenly and the temperature, but if you adjust it just right, you can get to the triple point. And that's also a function of the strength of the intermolecular forces between the molecules. So be able to interpret this graph and be able to answer some questions relating to the phase diagram. Now, we're going to compare the specific phase diagrams of two substances, carbon dioxide and then water. So what you'll notice here is carbon dioxide under regular pressures actually sublimes, so it goes from a solid directly to a gas. The triple point is actually quite high, and we've seen this. Remember, carbon dioxide has a solid form called dry ice. So that dry ice, under 1 atmosphere of pressure, dry ice is about negative 78 degrees Celsius, and if you just let it go at room temperature, it'll become a gas. So that's where you see this transition from a solid to a gas under regular conditions. However, if you want it to become a liquid, you have to increase the pressure to about 5 atmospheres. At about 5 atmospheres, it'll actually become a liquid. Anything higher than that, and then it'll become a liquid. So if you want to get carbon dioxide to become a liquid, you have to have it under high pressure. And the higher the temperature, the higher the pressure you'll need. So actually, if you want to be at around room temperature, if you want to retain carbon dioxide and make it into a liquid around room temperature, which should be around, here, you have to get the pressure to be pretty high. You have to be able to have a device that withstands about 65 to 70 atmospheres of pressure if you want to be around 22, 25 degrees Celsius, which most containers will burst. But if you have a steel container, reinforced steel container, you can easily contain carbon dioxide gas, and that's exactly what fire extinguishers are. So fire extinguishers have very thick metallic walls, and you can have a pressure this high, and in that case, it actually remains a liquid. Carbon dioxide remains a liquid. So you'll see that it has a different shape compared to another phase diagram. So let's look at another phase diagram, which is good old H2O. So we know that water under 1 atmosphere conditions simply goes from a solid to a liquid. So we have regular melting, and then it'll go from a liquid to a gas at 100 degrees Celsius. So these, you can see from here also the boiling and the melting points of these substances. So the melting point is when you transition between the solid and the liquid, and that happens at 0 Celsius. The boiling point is when you transition from liquid to a gas, that happens at 100 Celsius. You can also see the point for that sublimation point for CO2 up above. Now, what you'll see is that an interesting feature of the phase diagram for water as compared to CO2 is that water has a negative slope. Notice you have a negative slope. If you look up above, for a CO2, the slope is actually positive. So you'll see this is a positive slope for CO2 for carbon dioxide. And this actually has an important connection to ice being less dense as a solid. So we know ice floats. If you have a glass of water, we know that ice cubes float on the glass of water. There's a little ice cube floating. And this is because ice as a solid is less dense than ice as a liquid. So anytime you increase the pressure, you're essentially squeezing the molecules closer together. You're forcing the molecules closer together. So say you're at a solid and you increase the pressure. As you increase the pressure of that solid, it will become a liquid. That's because liquid water is more dense. So you push the molecules closer together and they became a liquid, because particles, when they're closer, are liquids. Water is a liquid. Now with CO2, the opposite is true. So remember, this is the liquid. So if you have a liquid and you start increasing the pressure, remember this is the pressure. If you increase the pressure, it actually becomes a solid. So in the case of CO2, this transition line has a positive slope because CO2 is more dense as a solid versus a liquid. And this is true of most compounds. Most phase diagrams will have this be a positive slope because most phases, the solid is more dense compared to the liquid. So as you increase the pressure, you become a solid. Not so with water. Water is very unique in this regard. And in fact, this is why water, when it freezes, goes to the top of a lake, and this is a good thing, because if the opposite were true, if ice was more dense than water, then ice would sink to the bottom of a lake, and over winter time, you have a lake completely frozen from the bottom to the top because it freezes from the bottom. So you'd have layers and layers of ice. Eventually, the whole lake would be frozen, and number one, little fishies that are swimming around in the lake, here's a little fishy, would actually die, would freeze over, or all marine life technically would freeze over. And then number two, when the sun came out again in the springtime, in the summertime, it would maybe melt the top layer of the lake, but the bottom layers would remain frozen, and we would not be able to enjoy the wildlife. So there's actually a lot of very important features of this. So we are very thankful that water is less dense as a solid as compared to a liquid. And here's a little fox walking around a frozen pond or a body of water in the frozen areas of Siberia. So very important that water has this specific feature, and it's reflected on the phase diagram. All right, last idea here, and then we'll go on to solids. So from the phase diagrams that we've looked at, it says note the high critical temperature and pressure for water. In fact, the critical temperature and pressure for water, if I just skip back a second, we'll see that the critical temperature and pressure of water happens at 218 atm, right up here. This is, remember, the critical point, and 374 Celsius. So really, I mean, the temperature is not as high as the pressure, 218 atm. That is pretty significant. Remember, above this point, the liquid and the gas coexist. If you look at the same temperature and pressure for CO2, that happens at 73, still high, but nothing like water. And the temperature is, just slightly above room temperature. So water has a much higher critical point temperature and pressure as compared to CO2. And this is significant because water has much stronger intermolecular forces between its molecules. So remember, the water, the intermolecular forces, or van der Waals forces of water, especially, is hydrogen bonding. Water has a lot of hydrogen bonding, which means it also has dipole-dipole forces, and it also has small, weak, but it still has London dispersion forces. Whereas CO2 has only London dispersion forces, so it has weak forces, and so it'll have a low temperature and pressure to keep. It doesn't require a lot of temperature and pressure to keep its molecules together. That's kind of the idea. Now, CO2 is actually used, liquid CO2 is actually used as a solvent because it's pretty easy to attain those temperatures and pressures under, conditions that can be achieved and worked with. It's actually used as a solvent. Solvent meaning a medium that dissolves other things, and it's used to extract nonpolar substances. So anytime you want to extract something from a plant, they can actually use liquid CO2. So liquid CO2 is really important in industrial applications. What you see here, a graph of a transition from the regular phase of water and gas, so liquid and gas, into the supercritical fluid. So here we have, this is liquid, this is gas, water, gas. As you increase the pressure and as you increase the temperature, you slowly fuse the two together, and here is what you have. You have the supercritical state, where it all looks like one thing. Now, it looks a little blurry, but that's because it's at a high temperature and high pressure. But it all looks like one thing. So we'll show you a few videos of this happening in class. Right, so that completes the video 7, and we'll take a look at solids in video 8.